Every single second of every single day, there's this invisible, super high-speed journey happening all around us. It powers our entire world, but we almost never stop to think about it. Today, we're going to follow that journey. We're going to trace the path of power all the way from its source, across hundreds of miles, directly to you.
I mean, have you ever really thought about it? You just flick a tiny piece of plastic and boom, a room is instantly flooded with light. What command did you just give? And what exactly answered the call?
Well, that simple little act is actually the finish line of a massive, super coordinated relay race. So to really understand it, we've got to go all the way back to the beginning and meet the hero of our story.
And the hero of our story is the electron. It's this tiny, tiny particle, so small it's almost impossible to imagine. But when you get trillions and trillions of them moving together, they literally change the world. Because at its very core, that's all electricity really is. It isn't magic. It's just a huge, coordinated flow of these little particles. Think of it like a river, But instead of water, it's a current of electrons.
So everything you can see and touch is made of atoms. And inside those atoms, you've got your positive protons, your neutral neutrons, and then there's our hero, the negatively charged electron, just zipping around the outside. Now, here's the key. In certain materials, like metals, those electrons can be convinced to leave home and go on a little trip. That's the secret sauce.
Now, this flow of electrons isn't just random chaos. Nope, it follows some very specific rules. The physics that tell our electron hero how to get from point A to point B. Let's take a look at the three big ones.
First up is voltage. If our electrons are like water in a pipe, voltage is the pressure that's pushing them along. The more voltage, the stronger the push, and the more potential there is to get some work done. Next, you have current. We measure this in amperes or amps. This is the volume of the flow. It's how many electrons are actually passing by a single point every second. So, to keep it simple, voltage is the push and current is the flow.
And the third piece of the puzzle is resistance. See, not every material is a perfect superhighway. Resistance, which we measure in ohms, is kind of like friction, or a really narrow section of pipe that slows everything down. So together, these three give us the push, the flow, and the thing that tries to stop the flow. And here is where it all comes together so perfectly. These three ideas are linked by one beautiful, simple formula. Ohm's law. Voltage equals current times resistance. And trust me, this isn't just some boring equation from a textbook. This is the fundamental rulebook that lets engineers design everything from a simple light bulb to a super complex microchip. It's the key to controlling electricity itself.
Okay, so our electron knows the rules of the road, but what gives it that first massive push to even start its journey? Well, that's its call to adventure, and it all begins at the power plant.
One of the most common ways is by burning fuel, like natural gas, to boil water. This creates a ton of high-pressure steam.
Or you could use the incredible force of falling water rushing out of a dam. A more direct way is solar power, where special cells just convert sunlight itself straight into a flow of electrons. But for most of the other methods, there's a common link.
And right here, this is the unifying idea. Whether it's steam, or falling water, or even wind, the goal is pretty much always the same. Spin a giant wheel called a turbine. That turbine powers a generator, and it's the generator that finally gives our electrons the command to start moving.
So, once those electrons are on the move, their great migration begins. And this isn't a short little trip across the room. We're talking about an epic journey, sometimes across hundreds of miles, through a really complex network we call the grid.
The whole trip has 5 main stages. It starts with generation, right there at the plant. Then, it's sent through high-voltage transmission lines, those huge metal towers you see out in the countryside. At a substation near your town, that super high voltage gets lowered for safety. Then it's distributed on smaller, local power lines until it finally arrives at your home, ready for you to use.
So our electron hero has traveled hundreds of miles and is now just waiting. Right there, behind your wall outlet. It has reached its final destination and it's just waiting for a mission.
Now, the electricity in your walls is a special kind called alternating current, or AC, where the electrons actually wiggle back and forth really fast. It's used because it's way more efficient to send power over long distances. But your phone and your laptop, they use direct current, or DC. That's a steady, one-way flow. That big black brick on your laptop cord, that's just a converter. Its whole job is to change the wall's efficient AC into the DC that your device actually needs. And when you flip that switch, all you're doing is closing a circuit. You're completing the path, giving the electrons a clear road to travel from the outlet, through the wires, into the light bulb, which we call the load, and then all the way back again. The light bulb provides resistance, and that resistance is what causes the electron's energy to turn into light and heat. The journey is complete.
It's so easy to take this whole invisible journey for granted, but this flow of electrons, it's the lifeblood of our modern world. It powers our hospitals, our communication networks, our industries, our homes. Without it, life as we know it would literally just stop.
So, we've followed the electron from the generator all the way to the light bulb. But as we look to the future, to renewable energy and smart grids and all kinds of new technologies, this journey is far from over. The question now is, what will its next great migration look like?